In today's video, we will be talking about planetary motion. After watching this video, you should be able to understand Kepler's three laws and understand the relationship between a satellite and projectile motion. So let's get right into the lesson. The first of Kepler's laws I'd like to talk about is something called the law of ellipses. And it's actually pretty simple, pretty straightforward. Basically, the law of ellipses says that all planets orbiting the sun orbit in a path that's described as an ellipse. And basically, an ellipse I just kind of consider it to be like a funny shaped circle. So this would be like an example of an ellipse. All right? And I'm making this pretty, well, it's not a very good circle to start with, but pretty egg-shaped. Now, the planets, if you were to actually look at them orbiting around the sun, to our eyes, they would appear to be a perfect circle. But if you actually measure the distance from the sun to the Earth, say in January, and compare that distance from the sun to the Earth in July, 6 months later, the Earth is actually further away from the sun in July, believe it or not, compared to in January. So in an ellipse, there's basically this point here. It's called the focus, and this is where the sun would be if we're talking about like say our solar system, and then this would be like Earth orbiting around the sun. Okay, so it'd be kind of going around the sun, orbiting around this point called the focus. And so at some points in its orbit, it would be further away from the sun. So like say it's here, it'd be pretty far away from the sun. The distance there is longer than, say, like when it's here in its orbit, it's closer to the sun, okay? And that's basically all Kepler's first law says, is that all the planets orbit around the sun in an elliptical path or in the shape of an ellipse. It's not a perfect circle, okay? So you're not always the same distance from the sun. And that'll turn out to be kind of important later on as we go through things, all right? What's Kepler's second law, you may say? Well, that's a great question. Kepler's second law is dealing with basically the amount of area a planet sweeps out as it orbits around the sun. And I have a picture that will kind of help show this in just a second. So hang with me if this text confuses you. But basically, Kepler's second law is sometimes referred to the law of equal areas. And basically, it describes the speed at which a planet will orbit around the sun. And it says that basically a planet moves fastest when it's closest to the sun and slowest when it's furthest from the sun. So basically what it turns out to be is that Earth is closest to the sun in January, and so it'd be moving the fastest then, and it is furthest from the sun in July, and so it'd be moving the slowest at that point in time. Okay, so if an imaginary line were like drawn from the sun to the Earth, as that line sweeps out through space, the amount of area is equal. No matter what period of time it is, the amount of area is equal. And like I said, a picture will explain this a lot better in the next slide. So if you're confused, hang with me here. Let me get to a picture. Here's a nice picture of the law of equal areas. So basically, kind of going back to this idea, let's say this is the Earth in July, okay? Here we are in July, and we go through 30 days, and now here we are in August, okay? There's August. This area here, and I'll call it A1, is actually, believe it or not, equal to this area here, this teal piece here. Well, I'll call it A2. Actually, all the areas are equal, okay, because as long as it's the same amount of time. So if this took 30 days to go from here to there, and this took 30 days to go from here to here, those areas, those pieces of pie are equal. So it'd be kind of like if you cut up a pizza and you kind of cut it in weird shapes and stuff like that. Someone might complain and say, hey, you gave me this piece right here that seems smaller than the piece that Johnny got, but they're actually the same amount of pizza. The areas are equal. Something I was mentioning in the previous slide that I just want to kind of hammer home here is the Earth is actually moving fastest here in terms of its orbit as it orbits around the sun, and it would be slowest over here, okay, as it orbits around the sun. So keep that in mind. That's kind of an important thing to comprehend. And I have another picture that'll kind of help explain why that's the case. But it's actually moving fastest here, slowest over here. And this is all due to basically this elliptical shape in which the Earth is orbiting around the sun. So what is Kepler's third law? Well, Kepler's third law basically is referred to the law of harmony. And basically it compares the orbital period and radius of one planet to another planet. And frankly, I'll go into that a little bit more in the next video lesson because it deals with a little bit of math, nothing insanely hard. But this video I really want to just focus on presenting the three laws and giving you an idea of what they are. So basically Kepler's third law, referred to the law of harmonies, compares the orbital period and the radius of orbit of a planet to other planets. Okay, so there's some sort of relationship that's going on between the orbital period of, say, Mercury and the orbital period of Earth. There's a relationship there. So the fundamental principle to be understood here is that satellites are considered projectiles, okay, which is what we were talking about in previous lessons, talking about projectile motion. If you remember, an object undergoing projectile motion, the only force acting on it is gravity. And that's what a satellite is basically the only force acting on a satellite, whether it's the moon, a satellite man put up into outer space, or if it's Earth orbiting around the sun, the only force acting upon it is gravity. So it's not like the moon has some jet packs that turn on every now and then to keep it in orbit around the Earth. That's not the case. Basically, the force of gravity is what's causing the moon to stay in orbit around the Earth. So a question you may ask yourself is like, well, let's say I want to launch a satellite into space. Let's say I want to launch, we'll call it satellite Benny, into space. At what speed would I need to launch that satellite to make it orbit the Earth? Well, basically, it turns out that if you were to stand here and look across the Earth, every 8,000 meters, there is a 5-meter drop in the Earth, or the Earth curves downward 5 meters. And so that's kind of an important thing, and I'll explain why in just a second. Let me get to the next slide and show you a little bit of a formula to explain why that's important. Now, there's a lot of text on the slide. Don't freak out. Basically, the vertical distance that a horizontally launched projectile would fall in the first second turns out to be about 5 meters. Okay, and if you remember, the Earth curves 5 meters every 8,000 meters. So every 8,000 meters horizontally, the Earth curves downward 5 meters. And this can be just figured out basically by 1/2 times gravity times time squared. So if you launch a projectile with a speed of about 8,000 meters per second, and just to give you a rough idea of something that maybe is a number that you can relate to a little better, that's about 18,000 miles per hour, give or take a little bit. It would be capable of orbiting the Earth in a circular path, basically not taking into account air resistance and that type of stuff. So if there was no air resistance and no drag or anything like that from air, if you could, throw a ball at 18,000 miles per hour, you could put that baseball into orbit around the Earth. Kind of cool to think about. So at 8,000 meters per second, the projectile would drop about 5 meters towards the Earth in that 1 second. But what's interesting is, as that projectile travels 8,000 meters in that first second, even though it has fallen 5 meters, the curvature of the Earth has also dropped 5 meters. And so the projectile is still the same distance above the Earth. And so it's now basically following the curvature of the Earth. It never can fall fast enough to hit the ground. It just stays constantly above the Earth's surface, and that is what a satellite basically is. Is satellites are orbiting around the Earth. They're actually falling towards Earth, but as they travel horizontally and as they fall vertically, the Earth curves underneath it as it falls. And that's kind of a hard thing to wrap your mind around, so you might want to take a second to kind of think about that and see if you can kind of get your head to wrap around that idea. But again, basically, if you're traveling so fast that as you travel this horizontal distance and you fall towards the Earth itself is actually curving underneath you, and so you aren't able to ever actually touch the ground because it curves before you can actually fall and hit it, if that makes sense. So that's basically what a satellite is all about. Now, we had talked about basically circular motion, and that was dealing with objects that were undergoing motion in a perfect circle. I started this video off talking about that basically all the planets in our solar system are orbiting around the sun in a elliptical fashion. And so an ellipse, the motion in an ellipse is not always having the same speed. And I mentioned previously that if the this is the Earth here, so now we'll call this the moon. When the moon is in orbit around the Earth, it's traveling actually the fastest here and the slowest over here. And how do I know that? Well, at this point, the moon is further away from the Earth than, say, at this point here where I wrote fast. It's actually closer to the Earth. So when it's closer to the object that's orbiting, it's going to be moving faster. And when it's further from the object, it's going to be moving slower. And you may say, well, how come? Well, the reason why is, if you remember from circular motion, there's always a net force towards the center of the circle. And in an ellipse, the net force is towards the central object. So here you can see F net is pointing towards the Earth, F net pointing towards the Earth, F net pointing towards the Earth, and so forth. When the moon is going around the Earth in this motion, and you notice its velocity is going relatively left, the net force is not perfectly going towards the center, right? It's actually kind of back and to the right a little bit. So it's towards the center and to the right, I guess is how I should really say it. So if you were to break this net force into components, there is actually a component that is headed, let me change pen colors here, that is actually headed in the opposite direction that it's traveling. It's headed this direction. And so that net force is actually causing the velocity to slow down. Not so much change directions, but just slow down. And so as it gets finally to this point here, this is where it's the slowest, that the net force has slowed it down. But now if we look at the moon, say at this spot right here, notice the net force is towards the Earth still, yes, but a portion of it, a portion of this component of this vector would be moving this direction, right? And so that's going to cause the object to speed up. And so during this portion of the orbit, it's getting faster and faster and faster until finally it gets way over here, and now it's moving really, really fast, or I should, as fast as it can be going at that point. And then it starts to slow down again. And this cycle just continues to repeat over and over again. And that is why basically the Earth and any object orbiting in our solar system speeds up as it gets closer to the central body on which it orbits, and it slows down as it gets further away from the central body that it orbits. And when I say central body, that could be the Earth, the sun, whatever. It just depends on what the object is. All right. So in summary, if we were to kind of just wrap this baby up, satellites are considered projectiles. They basically orbit a central massive body, and instead of falling into it, they go around it because they're traveling at such a speed that by the time they start to fall towards the ground itself has curved underneath it. And we know that anything that's considered a projectile, quotes, basically the only force acting on that projectile is gravity. Okay? So what's kind of neat is the motion of satellites, like any projectile, whether it's a cannonball, the moon, whatever, is all governed by Newton's laws of motion. So Newton's laws really do extend beyond just this thing called Earth. They go out into the universe and beyond. All right? That takes care of this video. I will see you guys next time.